For this lesson, we're going to be taking a look at polynomials in what is probably a much more useful form than we've been looking at so far. Up until now, we've been looking at polynomials in an expanded form, which is a good way to get an idea about the order of the polynomial, and that will tell you some characteristics. But once you get into factored form, we can get a lot more specific about some of the information. So the first thing we're going to be looking at with respect to factored form is the same quality that we get from for example, a parabola in factored form, which is that you can use the factors to find the zeros. And that's an incredibly useful property for any kind of graph if we're trying to do a sketch, if we're trying to get an idea of what this thing looks like overall. And as we've seen previously, if you can come up even with a rough sketch of a polynomial, you can say a lot of things about it. So in this case, if you look at this carefully, you'll see that this is a constant a. I have x to the power 1 here, and this bracket is to the power 1, x to the power 1, and x to the power 1. Each of these brackets with the factors is also to the power 1, which means that the order of this polynomial is, this would be a cubic, the way I've expressed it here. Now, because it's in factored form, because I have something times something times something times something, if I want to know where the zeros are for this, I just set the polynomial, I set the function equal to 0, and I solve. And that's what I've done down here. So the constant, the leading coefficient, obviously it's not 0, it's a number. If it was the number 0, this whole thing would be 0, so that's not useful to us. So in this case, we're assuming correctly that the leading coefficient is not 0. And so in order for this product of 4 different factors to be equal to 0, well, that means that one of the factors that involves a variable has to be equal to 0. So this first factor, x minus p, must be equal to 0. In other words, x equals p. Or x minus q equals 0, which would give x equals q. X minus r equals 0 gives x equals r. And any of those being true, it doesn't require all of them to be true, any one of those being true will turn this whole thing into 0. So p, q, and r, the values p, q, and r all represent zeros. Now, the other thing to consider, so once again, I'm in factored form, but the other thing to consider is actually the order or the degree of individual factors, because that will tell you what the graph is going to look like around those zeros. So first of all, let's just focus on the zeros part. So in this case, I have, from this one, I have the factors. Here's my leading coefficient 5. I have the factors x equals 0. That's one of my zeros. X minus 1 would mean that I have a 0 at x equal 1. And x minus 2 as a factor means I have a 0 at x equals 2. And you can see I've got that already shown on the graph. This is a computer-generated graph of this function. So I have a 0 at 0. You can see it touches the x-axis there. I have a 0 at 1, and I have a 0 at 2. Now, what's interesting about this is the behavior of these zeros. And what that means is, what does the function look like as it is in the vicinity of this 0, or this 0, or this 0? And if you take a look at these, just think about them, they actually all look quite different. This one very much so, because this one is decreasing and it just touches the x-axis and then it turns around and is increasing. This one crosses the x-axis, and this one also crosses the x-axis, but these two, well, they do look somewhat different. Now what I want to do is I'm actually going to zoom in on each of these to show you and talk about why. But what I'm claiming is that the order, which would be, this is an x squared, so this x equals 0 came out of an x squared. This x minus 1 is to the power 1, and this x minus 2 is to the power 3. So if we talk about the order of these zeros, this x equals 0 came from an order 2, 0. This x equals 1 came from an order 1, 0. And this x equal 2 came from an order 3, 0. So let's take a closer look at these and try to understand the implications of that. Why do they look the way they do? Okay, so the first one, x squared, which is order 2. If we zoom in on this area, you can see what we have is this shape. This one you can actually see pretty well just from the graph. So if we zoom in here, and you can see from my scale, I'm much closer. So this one is order 2, and what does this shape look like? It's not exactly, but what does it look like? Well, to me it most looks like a parabola. And a parabola is also an order 2 polynomial. So if your 0 is an order 2, then the behavior at that 0 is going to be an order 2. So the behavior in this case would be a quadratic, which would be looking like a parabola. So if that follows, then if we take a look at this second one, which is at x minus 1, that is order 1, because there's no exponent explicitly written here, so the implied exponent is an exponent of 1. And what does it mean to be an order 1? Order 1 is linear. And you can pretty much see this from the graph, but the more you zoom in, if we zoomed in more and more and more, the more that would look just like a straight line. So there's a linear behavior occurring there. And then finally, you can probably anticipate this one, this last factor, x minus 2, is to the power 3. So that means it is an order 3 factor. And so its behavior is going to be cubic. Not so easy to see here, but if I focus on more of the beginning and end of it by zooming in, you can see that's the standard shape of the parent function y equal x cubed. Okay? So if you are given something in factored form and you are asked to sketch it, your sketch can actually, even without worrying about getting the scale, well, you should be able to get the scale correct when it comes to the location of the zeros. And from there, you should be able to say things about how does the function start and end. We've talked about that in terms of vertical reflections. And then you can actually start to get into some pretty sophisticated predictions about how is the function going to look at the zeros. And putting all of those things together is going to let you come up with a pretty good estimation of the overall look of this graph. No, you're not going to know what these maximums and minimums are. Those are just going to be guesses. You're just going to sketch those. We're not really worrying about vertical scale very much, but you should be able to come up with a pretty good representation of the overall shape. So if we are sketching the graph of a polynomial, this is a bit of a recap of what I've just said. So first thing we want to do is look at the leading coefficient, figure out whether or not there's been a vertical reflection. And then we look at the order of the polynomial, because we know that even and odd ordered polynomials have different behaviors. So that's going to tell us our end behavior. From our factored form, we're going to be able to get our x-intercepts, or our zeros. And don't forget, for finding your y-intercept, that's simple. All you're going to do is you're going to set x equal to 0, and you're going to find out what your y-intercept is. So that's an easy one to do straight from the equation, whether it's factored form or expanded form. And this last thing that I'm adding today, which is this idea of the order of the factors, is going to give you an idea of behavior. What I actually would recommend is when you're doing this, once you've identified your zeros, so put dots where you have zeros, and then if you know your end behavior, for example, you need to know your end behavior to know whether or not this parabola is above the x-axis or maybe it was below the x-axis. So once you know your end behavior, what I actually recommend you do is you sketch in that the behavior at the zeros for each of the zeros, and then come back and fill in the curve that would allow you to connect those zero behaviors together. And that's just my advice, but I've done this a couple times, so you might want to listen. Now, what if we go the other way? What if we are given a graph? And in general, if I give you a graph, I'll give you some scale, so you'll have, you should be able to pick off points that are actually good points, not just the zeros, but the y-intercept, and maybe you might even be able to pick off a maximum or a minimum or something along those lines. So the first thing you're going to do, just like if you had a parabola, you would use the zeros from there and you just sub that into your equation. Then, looking at the behavior around the zeros, you're going to be able to make a prediction about what each of the factors, what order they should have. And then you're going to sub in a point in order to find a leading coefficient, which is something that is a pretty standard procedure for determining an equation of any graph. Now, the best way to do these things is going to be to practice. So we've got quite a large set of homework here. A lot of these questions are just sketches, though. The sketches, you need to start with those, I think, because that gives you a better feel for things. But then make sure that you're also put a lot of effort into getting any equations when you're creating an equation, getting that correct, because that's by far the more difficult of the two. And that's it for this lesson on polynomials in factored form.